Okay. Can you guys see my screen?
Yeah.
Okay, excellent.
Yeah.
Okay, so chemistry is just basically the study of matter. Everything has mass associated with it. And now, when we think about mass, there's a lot, or when we think about matter in general, we think about it in three different ways. We think about what we can see. So that's going to be macroscopically. We think about things that we need a microscope to see with. So basically, that's going to be like cells and things like that. Macro meaning big. So macroscopically meaning like, a building or me or your ring or things like that. And we also think about it in terms of the particulate, things that are so small that we can't use a normal microscope to see. We have to use a specialized microscope, such as an electron microscope or a scanning tunneling microscope, so that we can actually visualize it. Okay, and so down here you can kind of see the scales. So things like, as I said, me, piece of paper, ring, a CD. You guys probably don't know what those things are anymore, right? Nobody knows what a CD is anymore. Microscopically are those small things that we need a microscope to see. Those are like plant cells, animal cells, viruses, things like that. And then the particulate is those things that we need that specialized microscope. See? And then that's like your atom and your molecules. So how many of you guys have really, really good eyes? Like your eyes are like the best.
Definitely not me.
Anybody?
Obviously not.
No.
With most things, yes.
Most things, yes. So are your
Well,
eyes so
if
good?
it's close to me.
Oh, what was that? Unless it's close?
Yeah, if it's close to me, yes. But if it's like more than a foot from my face, I can't see it.
Okay. So I'm going to test that vision here in a second. Okay. So are your eyes so good that you can see a single water molecule?
No.
Anybody?
Probably not.
I'm gonna say no.
Okay. So because we can't visually see a single water molecule, nor can we have the convenience of having, electron microscopes in all of our houses so that we can see a single molecule of water. So as chemists, we often have to use models to sit there and help us see things, right? And understand how things are going to be working. Okay. So there are two types of models that are typically used in chemistry. Get my screen to turn. Maybe. Okay. So we have what we call the ball and stick model. Why do you think it's called ball and stick?
It looks like a ball and a stick.
Because it's balls and sticks, right? So that's the ball and stick model. You guys can kind of see those nicely, right? So the ball and stick model helps us see the three-dimensional aspect of the chemical structure. And so a lot of chemistry, believe it or not, has a lot to do with the geometry, right? You thought you guys were going to get rid of geometry, right? So it has a lot to do with the geometry of the structure, how things are going to react and how they're going to behave when they're put with other chemicals. Okay, and so it's going to be important that we know that there's a 3D structure associated. So that's often why the ball and stick model is very important to us. Okay, so we also have what we call the space filling model. The space filling model, that just basically is often used on computer programs. And as you can see, it just fills up space, big, gigantic balls that are touching each other, filling up the space. So this chemical, or this molecule, CH4, this is called methane. Methane is composed of carbon and hydrogen. Now, if you notice, as a chemist, I just put CH4. So those are called symbols. Those are symbols to let me know what atoms are involved in this particular molecule. Here, we know that there's one carbon and there's 4 hydrogens that make up this molecule. And they're bonded together. So that's the reason why we write them together. Okay? So we have, in this case, this would be 1, and it's always understood to be a 1 molecule of carbon, of methane. Okay? So down here is just like a simple drawing of it, kind of showing the 3D structure. Of course, this is the ball and stick model. Now in chemistry, to kind of help us keep things clear, we often will associate with colors with certain atoms. So black will often be carbon. White will often be hydrogen. Red will often be oxygen. And those are the only ones I know off the top of my head. Okay, so a lot of times you'll see that consistently shown throughout the text. Okay, questions, concerns? Cash. Okay, so like I said, we often will use symbols to sit there and let us know what atoms we're talking about. Carbon is different than hydrogen. Methane is different than oxygen, you know? So they're gonna behave differently, so we need to be able to know the difference. What is the symbol for water?
H2O.
H2O, right? Everybody knows the symbol for water, right? H2O. Okay, so that means water is composed of 2 hydrogens and 1 oxygen. This here is called the subscript. Subscripts lets us know how many of that particular atom are in our compound, okay? And I'll be using terms like compound, molecules, and I'll explain it a little more in detail here in a second. And then we also know that there's 1 oxygen because it's understood to be 1. Okay? So, how many of you guys know all of the elements on the periodic table? There's about 118 different elements.
No.
No, you don't have them memorized? Weren't you supposed to have those memorized last week before school started?
No.
Yeah, no.
No. Okay, so that brings us to a couple of things. So for the students in Kalinga, because I really have control of your kits, in your kit, you guys are going to get a little packet, and that packet is going to be the same packet that you guys have under modules. So under modules, if you go down to resources, it has a periodic table, it has a polyatomic ion sheet, it has a conversion sheet. Your packet is going to have all those things printed out. The students in Harnell, I'm sorry, I don't control your lab kits. I'm going to work on it, so they'll be added to it in the future if I continue working there. But you'll be able to download it, right? All the resources, and these are going to be your kind of your bread and butter tools, because I'm not big on memorizing. I think the way that you memorize is by using, and I give you a lot of homework assignments to kind of help you memorize in a sense. So by the end of the semester, you should know that O is oxygen, C is carbon, and B is boron. And you won't make mistake of B being beryllium or carbon being Cl or anything like that, right? So, and the way that you're going to do that is by exposure, okay? So you guys can you guys see the periodic table there?
Yes.
Okay, good. So this is the periodic table. Here on the periodic table, this basically represents that letter represents the symbol for that particular element, okay? So H, hydrogen. So that number up at the very top is the atomic number, okay? And the atomic number represents the number of protons. So an atom is composed of protons, and electrons, and neutrons. Protons are positive, electrons are negative, and neutrons, they're neutral. Okay? Okay, so I'm also going to take you to P-table. P-table is my favorite site. It's kind of like porn for chemists. And you're like, so what is so exciting about this? Well, one thing, as you run over it, each element, it'll actually give you all the information about that element on the side. So it tells me the electronegativity, it tells me the melting point, it tells me the boiling point, it tells me the electron affinity, it tells me the ionization energy. So it tells me all of those good things just by running over it, right? We go up here. These are the properties that are associated with each of the different elements. This will let us know the electrons that are associated with the different elements. This will tell me all the different isotopes. This will tell me some of the compounds that these guys will be in, okay? So I'm very fond of P-table, so I'll often make reference to it, and I'll often click over here, okay? So I'm gonna ask you a hard question, because I know I'm talking very fast, and I know that you guys are listening to every word that I'm saying. So, aluminum. So what is the chemical symbol for aluminum?
AL.
Al.
So how many protons does aluminum have?
13.
13.
Okay, good job. Okay, and how did you know that?
Because it has it right there.
Atomic number.
Just right there.
The atomic
Right on
number.
top.
The atomic number, that's right. Okay, so because every element on the periodic table, when it's shown on the periodic table, is neutral in charge, so that means that the number of protons are going to be equal to the number of electrons. So for instance, if somebody just writes H and they ask you, well, how many protons does H have?
One.
Then how many electrons does H have?
One.
Okay, because it has to be neutral since it's just H. Now, when it has a charge, that's going to be different, and we'll be talking about that here in a little bit later. I'm just trying to get you guys introduced to a couple of topics here. Okay, how you feeling so far? Not too hard?
So how do you find the neutrons?
We'll get to that. I'm saving it. Okay,
Okay.
but that's a good question. Okay, so we're only going to talk about the protons and electrons right now. We'll get to the neutrons. I promise you we will. Okay, so let me clear this. Okay, so we have different states of matter, right? So I have water here, right? So what happens if I freeze water?
Solid.
What was that?
It's solid.
It becomes
Sorry,
solid.
I
What
didn't
is that
get the
solid
question.
called? What do we call that
I don't
solid?
under,
Ice.
Ice. Okay,
Mhm.
so if I freeze water, I make ice, right? And ice is a
Yeah.
solid, okay? If I boil water, what happens?
the gas, the
It
steam.
starts to evaporate, then turns to gas.
It turns to gas, okay? So let's think about this. So ice is a solid. So if I
Mhm.
melt ice, then I can make water. And then if I can make
Yeah.
water, water is a liquid, right? And then if I
Mhm.
boil water, I can make a gas. Now, can I ask you a question?
Yeah.
I want you to think about it. It's really hard. Okay, so what is the chemical symbol for water?
H2O.
H2O.
What is the chemical symbol for ice?
H2O.
H2O. H2O.
And then what is the chemical symbol for steam?
H2O.
H2O.
Okay, so water, steam, and ice all have the same chemical symbol. How can I distinguish between them? Chemically,
Physical. Physically.
okay? So the way that we do that, often, we will put an S for solid,
Gas and then
Yeah.
liquid.
an L for liquid, and a G for gas. Okay? So now let's think about this a little bit too. How many of you guys have gone to the beach? Anybody gone to the beach?
Yeah.
Yeah,
Okay.
yeah.
You guys play in the sand when you go to the beach and everything like that? Or do you go into the water?
Yes.
I
Okay.
don't go into the water.
Into the water. Have you ever been to a beach where the sand is so hot? Like
Yes.
really, really
Yeah.
hot?
No.
Yeah.
It burns your feet.
No.
It burns your feet. Okay. So now if the sand is really hot, right? What are you
Yeah.
gonna do
Yes.
Are you gonna run to the water? Are you gonna walk to the water? Or are you gonna, you know,
Run.
Run.
You run to the water.
why are you running?
That's hot.
That's
The
hot.
sun's
Because it's
hot.
hot, right?
Hot.
Okay,
Yeah.
okay, so let's think about this. So when we talk about molecules, molecules are kind of like you, right? So in the case of the solid, things are moving. So molecules are always moving unless we get to absolute zero, which I'll talk to you guys about here in a few minutes or a few lectures. But molecules are constantly moving. When it's a solid, they're moving just a little bit. Have you guys been to a nightclub? Anybody been to a nightclub?
Yeah.
It's
Okay.
gonna be.
When there's a
Been a
whole
while.
bunch of people in a nightclub, I mean, I know it doesn't happen anymore because of COVID, you know, but when there's a whole bunch of people in a nightclub, can you dance? Can you really dance, or are you just doing,
No,
just
You're staying in one
bobbing?
place.
The shoulder to shoulder.
That's right. So you're just doing that little movement, right? That little cute movement. You're looking cute. You're doing, you know, that's all you're doing, right? So that's kind of like what's happening with the solid. That solid is just doing that little cute movement. Got a little cute, right? And then as the dance floor, you know, less people get on the dance floor, you're able to move a little bit more, right? You know, you kind of get that, right?
Mhm.
Okay, so that's kind of like the liquid. Now the difference between the solid and the liquid is that it kind of heats up, and then you also start sweating a little bit, right? When you're starting to move a little bit more. So
Yeah.
that is part of the kinetic molecular theory. The fact that the molecules are moving. Molecules are constantly in motion. When they're solid, they just have very little motion, so like a vibration. When it's a liquid, you're kind of free to move, but everything is still kind of touching each other. And then when you're a gas, it's kind of like an empty dance floor. So you're just bouncing off the walls, right? And so you're able to move all over the place. It's constant movement, okay?
Can I ask a question? Can I ask a question?
Yes.
Okay. This reason for the freer movement in the liquid, is it because there are less molecules or because the bond is weaker?
Okay, so it is nothing to do with the bond. It's not, I should say, let me take this back. Let me give you the right definition. So what we have, what we call forces, different types of forces. A bond is considered to be an intra meaning inside the molecule, that type of force. And then we have intra, let's say intra and inter. Inter meaning inside the molecule, and intra meaning across different molecules. So those are interactions. So what's kind of helping them in terms of that connectedness is those interactions. Okay, and we will be talking about that. We'll talk about it a little bit more later on than now. But what's really doing it, right? So you're not breaking bonds. Bonds are not being broken because look here. Is water changing? Isn't it H2O here in the case of ice?
Oh, okay.
It's the same.
And then when it's
It's the
water,
same.
it's the same, right?
It's the same.
Yeah.
Okay.
And then when it's gas,
It's the same.
It's the same.
okay, or steam,
Yeah.
it's all the same. So chemically, it is the same thing. There's no chemical change. This is only a physical change. You're going from ice, because isn't ice different than water?
No, it's the same.
No.
Chemically, it's the same, but the state is different, right?
Mhm.
Right? Because ice is a chunk, right? And water is a liquid that can be moved around, and you know, I could throw a piece of ice and hit you in the head. If I throw water on it, it just runs all down your body, right?
No. Okay. Okay, not to drag the issue too long. I don't know. Okay, what is the reason for this change in state? What is the particular reason for what
So-
happens when
So what do you
it's no
think is the
longer solid?
particular reason? Why does ice become water?
Because of heat.
Yes.
Heat was
Because of
applied.
what? What was that?
Heat was applied. There was a
temperature, right?
change.
Oh,
Yeah,
okay.
the
So
temperature.
you're telling me,
Temperature.
so as temperature increases, molecules are going to move faster, right? Kind of like you on that beach. When temperature increases,
Oh,
molecules move
I get
faster
it.
because you're going to run to the
Yeah,
water as it gets
Okay.
hotter, right?
okay. Yeah. Get it.
Okay, so we've talked about gases, we talked about liquids, and we talked about solids. Now let's talk a little bit more about solids, right? So there's two types of solids. One is called a crystalline solid and one is called an amorphous solid. A crystalline solid is the solid that's really organized. It has a pattern that's associated with it. It has a great organization. Amorphous, how many of you guys are like sci-fi geeks like me? Like sci-fi movies? What is a morph? If something is considered to
Solid.
morph,
It's like a pattern.
It's changing.
it's changing, right?
It changes.
Yeah, so changes shape, okay? So amorphous basically means, A means lack. So it lacks shape or it lacks the ability. So it's not organized. It's all over the place. It's a hot mess, okay? So crystalline, organized, amorphous, unorganized. Oops, got carried away. Okay, so this basically is a slide that just tells you everything that we just talked about. Now you just can see the pretty pictures. Okay, so we have gas here, right? So gas and steam, you can see the molecules are going everywhere and they're going out of the thing. And you guys boil water. I always overboil my water. I boil it dry and then the whole room is all steamed up, right? Does steam just stand right above the pot or does it go encompass the entire?
It goes everywhere.
Everywhere.
It goes everywhere, right?
Goes everywhere.
Okay, because it's able to sit there and move and constantly moving and it'll occupy that whole space, right? So like after you take a shower, you see steam all in the room, it's all steamed up, right? Liquid is only going to occupy that volume that it's in to the point that it can occupy, right? Just like my little water here. And then a solid, you know, it's that ice tray. You get that cube, it's going to be rigid, it's going to be fixed. Pretty simple.
Yeah.
Yes.
Mm-hmm.
Yes.
Yeah.
So these are considered physical changes. So because you're not changing the chemical state of it, right? So it's water, it's water, it's water. It's always going to be water. There's no change. Okay. Simple.
Yes.
Okay. Okay. Let's see. We're getting tight. I have to finish one more thing, one more slide. I have to get you to
And
the
then
same
I
point.
have a question once you're finished with, yep, it's about the sugar once you're done.
About the sugar.
The sugar and the salt, I couldn't, I've been reading, YouTubing, and I just can't figure out why the salt being dissolved is a chemical change versus the sugar being dissolved in water is only a physical change.
Good questions. I love that. Okay, we'll get to that. Okay, so this is sucrose. Sucrose is a sugar. This is the chemical structure of sucrose. I'm messing up. C12 H22 O11. Okay, carbon, chemical symbol for carbon is just C. And then what's the chemical symbol for water again?
H2O.
So,
Okay. So here, this here represents one molecule of sugar. Now, there's a law that you guys are going to need to know called the law of conservation. The law of conservation basically says, I'm just going to boil it down, simple terms and anything like that. What you put in, you must get out. Okay? What you put in, you must get out. Okay, so here, this tells me I have 12 carbons. So that means if this reaction happens, this chemical reaction happens, then I'm going to have 12 carbons. Okay, so this here is the subscript. It lets me know in this molecule, one molecule of sucrose, there are 12 carbons. Okay, there's 22 hydrogens and there's 11 oxygens. Okay, now if what I put in, I must get out, that means in terms of the hydrogens and the oxygens, it has to be the same. So if I have 11 water molecules, that'll give me 22 hydrogens, as 11 times 2 is 22, and 11 times, this is understood to be a 1 since there's no number there. So 11 times 1 is what? 11. 11. Okay,
Yeah.
So then what I put in, I must get out. So this is considered to be a balanced chemical equation. This line here, this arrow, we refer to as a yield. And what yield means, it means that it makes. So we made carbon and water from this reaction. So how many guys have cooked sugar? Have you guys made caramels before?
Yes.
Yes.
So I tried to make some homemade caramels, which basically is sugar, butter, and milk, right? So I put my sugar in there to kind of get it to melt, right? And it started caramelizing and things like that, and I wasn't paying attention. And then by the time that I left, I ended up with just burnt sugar, which is just carbon and water. The water turns into steam and evaporates off, and then all you're left there is just the carbon broken down. So, can I get sugar from this?
No.
Can I make it back to that nice, clear, white stuff that I started out with?
No.
Okay, so that lets you know that this is a chemical reaction because I can't reverse it. Now I get two different other things. I get carbon and water. So that's a chemical reaction. Compared to when I boiled water and got steam, I didn't break those bonds. There wasn't a chemical reaction. That's a physical reaction. Okay, you guys got that?
Yes.
Good. Okay, so have a question for you, and then we'll stop, and then we'll go to the lab section because I figure there are going to be people hanging out there.
Dr. Henry.
Yep.
In the book, it says that chemical change, it says a change in color is often evidence that a chemical change occurred. So is that always the thing? So if every time there's a color change, it's a chemical change?
Yes and no. We will talk about that here in a minute, okay? Because there are certain ways that we can also do it. Sometimes you just have two colors that are mixed together, and if you separate them, you'll end up with one color and the other. So that's not necessarily a chemical. Okay. So, but that's a good question. Okay. So chemical or physical. Okay, so we're gonna do a quick poll here. We'll see if you guys got an understanding. And then we'll talk about the sugar. You know, it's all about the sugar. Okay. So, can I get to my slide? There we go. Okay. So the very first one, let me tell you what's going on. So we have this log burning. Okay, log burning. Is that a chemical change? Is that a physical change? Is it both, or is it neither?
Sorry, can you
It's a
come again?
chemical reaction.
What's the question?
Yep. So there's a
Okay,
poll
the question,
going on.
please.
You guys get the vote.
Yeah.
The question is, and A, is that a chemical change? Is it a physical change? Or is it both or neither?
Sorry, I didn't get what you're actually talking about. What is actually going to be chemical or physical? I didn't get the question.
The question is, this log burning, is that a chemical change? Is it a physical change? Is it both or is it either? Do you see the very first slide? A.
Okay.
Yeah.
Physical.
I think it's chemical, but I closed the
Chemical,
poll. and
actually.
It's
It's chemical because it burns and you won't get
It's
the
chemical
object back.
because it's burning.
Okay, so
The
everybody,
substance is
okay,
destroyed and
okay.
a new
Now you guys
substance
all
is
told me.
made.
Now, did you guys vote on your poll?
Wait,
Yeah.
okay,
Yeah.
I closed the
did.
poll and I don't know how to get it back.
Hit poll.
Hit poll.
Hit poll. There should be at the bottom. There should be if you or that, there should be something that says poll.
Oh, okay, it's black.
Okay. So everybody got their vote in, right?
Yes.
Yeah.
Yes.
Okay. So I'm gonna ask you a question. So if I burn a log, can I use those ashes and the smoke and everything to make a log?
No.
No.
No?
No.
So
Yeah.
is that a
No.
chemical change or is that a physical change?
A
Chemical.
chemical change.
Chemical change.
It is a chemical change. Okay. Okay.
I have a question.
Yep.
Okay. Grinding sugar to powder, is it a chemical change or physical?
Are we changing the physical state? Or are we changing the chemical state of the sugar?
That's what I can't fathom. Like that you're actually grinding it, so I feel maybe the molecules are
Okay. So
okay.
let me ask you
You're not-
this. So you
okay.
grind it, right?
Okay.
Now you take that grinded
Yes.
sugar and you taste it. Does it still taste like
Yeah.
sugar?
Yeah. Yeah, definitely.
So then it's sugar, right?
It tastes. Yeah.
So the only
sugar.
thing is that you're just making it
Okay.
into smaller molecules of it, right? Or smaller
Okay.
chunks of it.
Okay.
Okay. B, ice melting. Put your vote in.
Yeah.
Okay. So the correct answer is, can we take that water and change it back to ice?
Yes.
Yes.
What temperature?
So physical,
Yes.
so that's a physical reaction or a physical change.
Yeah.
Okay, what about a glow stick? After you crack open that glow stick, what happens?
That's a
Chemical.
chemical reaction.
Okay, so when we crack open that glow stick, and if we let it sit for long enough, like a day or so, are you able to get it to glow anymore? Or is it just done?
No.
No,
It's
you
done.
can't.
No, it's done.
It's one and done, right? So then that's also an example of a chemical reaction. So simple.
Yes.
So far,
Okay,
yes.
so let's stop here. And then what we're going to do is we're going to go to the lab session. But before we go to the lab session, there was a question about sugar, say salt versus sugar in water. Okay. Let's stop my sharing. Okay. So Shikuria brought up a question. So salt in water versus sugar in water. She says she read somewhere that salt in water is a chemical reaction, where sugar in water isn't. It's a physical
Would
reaction.
this be a better question for lab?
Oh, this will be a great question for lab. Okay, so let's, you guys are thinking about it, right?
Mm-hmm.
Okay. Now, let me tell you what's happening under both circumstances. Okay, so this here is the sugar molecule. So this sugar molecule looks something like this. If I can remember it right. Each of these corners represents a carbon. Okay, so the sugar looks something like this. Now, the bonds here between the hydrogens, the oxygens, and the carbons. So these guys represent carbons. There's all of these hydrogens. I'm not showing you all of the hydrogens. I'm just showing you a few of them. Now, they're physically connected to each other. They're kind of like your arm. They're physically connected that way, right? So they're not taken apart, okay? Now, these guys are going to be able to interact with water. The water molecule, which looks like this, OH. And because of the characteristics of water, it's going to allow it to go in suspension. So if we have our water here, you have your water, you put a little bit of sugar in there. So the water is going to be able to surround the sugar, and based upon the characteristics of the water and the sugar, it's going to keep it in suspension. Now, if we let this sit for a couple of days, and hopefully we allow the water to evaporate, so we put a little bit of heat under it, what's going to happen is that we're going to get the sugar exactly back. So the sugar is going to have no change to it at all. Okay, so in this case, you just have a solution that has been mixed. So we have a solution of sugar and water. And so, and there are ways that we could actually separate by heat. We could separate the water from the sugar. Okay, so this is considered to be a physical reaction or just a suspension, right? Now, we take salt and water. Salt is sodium chloride. Now, sodium is a metal. It's a very reactive metal. And chloride is it's a halogen gas that is very active too. So halogens are very active and those metals are very active. But when you put them together, we get something that we can actually eat and that tastes great on food, right? Salt. So now what's happening, because sodium, where sodium is located on the periodic table, it wants to be like a noble gas. Let me go to the periodic table so you guys will know what the noble gases are. And I'll explain to you why it wants to be like the noble gases in probably the next lecture or so. Okay, sodium is located here. The noble gas is right here, right? Now what sodium does, sodium will lose an electron so that it will be like this noble gas neon. Because being like the noble gases, the noble gases are stable. And at the end of the day, this is all about stability, low energy and stability, being lazy and being rich, or being happy with things that you have, right? So these guys, these noble gases are happy with what they have. They're stable. These guys, when they're in their natural state, they're not stable. So they're trying to find a way to become stable. And the way sodium can become stable is by losing a single electron, which causes it to be Na+.
Excuse me, Dr. Henry, are you showing us the periodic table? We just see like your tabs and stuff in the slideshow.
Oh, okay, I'm showing you the periodic table. Let me see why it's not showing you the right thing. Okay, how about now?
Yeah.
Thank you.
Yeah.
This is what happens when you have like two screens going on here. Okay, so sodium is here, neon is here, right? So for sodium to be like neon, it has to lose a single electron. And the way it does that is by donating it or giving it away, okay? So it'll actually give it away. Chlorine is here, and it wants to be like argon by gaining a single electron. So if it gains one more electron, it's going to be like argon. So when you get sodium chloride together, sodium becomes Na plus, and it donates its electron to chlorine, and then chlorine becomes Cl minus. Now, how many of you guys dated when you were in high school?
Oh, sorry.
Anybody dated when you were in high school?
Me.
Okay, so was there that really, since all I heard were women answer that, that really hot guy that you liked and you're like, oh, he is gorgeous, right? But he was really bad and you're a really good girl. I mean, Erin has that look on her face. She already has that look like she was one of those girls that were a good girl and there was that bad boy. No?
Oh yeah.
Oh yeah. Okay, good. So now you guys got together at opposite attract, right? He liked you, you liked him, opposites attract. And you went home and your mom was like, oh no, that boy's bad. His dad was bad, you know, all that. And you're like, but no, I love him. He's the one I'm gonna marry and have my 20 kids, right?
Yep. And now you have a 13-year-old with him.
Okay, so in that case, those opposites attract. That's the same thing that's happening here. These are called ions because they're charged. Either charged molecules or charged atoms, they're called ions. This has a plus charge, this guy has a minus charge, and so they'll come together and they'll interact together to balance each other out because they want to be stable, and they form sodium chloride. So that's what's happening in that case. Now, when you put water in there, water has a weird characteristic. It can be partially charged, not completely charged. So it won't have a complete charge associated with it, but just a slightly positive and a slightly negative. So part of it will be slightly positive, and the other part will be slightly negative. So we have OH, and I'll explain this in more details later on. So the hydrogens are considered to be partially. This symbol here means like partial, plus, and the oxygen are going to be partial minuses, right? Not complete, but just partial. Now, it has kind of like a bipolar personality. You have a plus and a minus. So that plus can interact with the chlorine, and the minus can interact with sodium. So water acts like a home wrecker, right? It goes up to sodium and said, hey, baby, you don't need chlorine. He's no good for you, right? Let me take care of you, right? So then the oxygen is going to interact with that sodium, that positive charged sodium. And then the hydrogen is going to go up to chlorine and says, you don't need that girl. She ain't no good for you. Let me take care of you, okay? So water is a home wrecker, right? It splits up the two. So the reason why salt dissolves in water is because you're allowing those charges to split up. You're separating the chlorine ion and the sodium ion from each other. When they're together, they form that solid, but when they're apart, they're just forming the ions that are stuck in solution, surrounded by water, keeping it in solution. So this is considered a chemical reaction where when you put sugar in there, because you're not breaking up the sugar, it's still connected. That's considered to be a physical reaction or a physical event. And we'll talk about this again. Like this is the very beginning, and it isn't going to be all clear because you don't know enough about ions and partial charges and partially positive charge and partially negative charge or the periodic table yet. But you're going to learn all of that, I promise. Okay. Then you'll be saying, this is a piece of cake. Okay. Questions, concerns, Cash?
I think what confused me more was because they were saying that you can heat up the sugar and then get sugar again.
Yep.
But then you can also heat up the salt water and also get the salt again.
Yeah, and you can. And the reason why is because they're positive and negative, so they're going to come back together because water's no longer there to keep them separate, even though that it is a chemical reaction because you're separating those two.
So the formula that you made earlier, would that have to do with like the mixtures and the pure?
Yes, yes,
Okay.
and we will be talking about that on Thursday. Yeah, I like that. You're ahead of the game. I really like that.
Wait, just a little question. Is the charges at the end of water, isn't that called like polarity?
Yes, that is called polarity.
Okay.
Yeah. Okay.